Hello and welcome back to Differential Equations, section 1.5 on first order linear equations. So we talked about linear equations, linearity and linearity for equations at some point earlier. And today we're going to put some kind of a general formula and take a look at two methods in this section. One will be a method of integrating factor, and the other one is the constant coefficient real quick, a formula, and you're done. So some of the first order differential equations are separable. So you don't need any of the scary methods, right? You can just separate, integrate both sides, and be done with just seeing one of the easy examples on logistic equation, right? But in general, what we are looking at as a formula is going to be, so theorem 1, the linear first order equation, let me write it in blood, dy dx, right, that will be the derivative, plus some kind of function p of x times y equals capital Q of x, another function, and we would have initial condition so that we can have particular solution. Without initial condition, you just have the general solution. So this is an equation, differential equation. We do see the first derivative, which is dy dx, and this is going to be functions p and q, could be numbers, could be functions. It's linear because your dy dx is not multiplied by any other function, right? It's just dy dx. It's first order, which is why it's a first order. And the way to solve this is we are going to use something that it's called integrating factor. If you take a look on the left-hand side, it looks almost as unfinished product rule for from a Calc 1 class, right? If I am to write that product rule, say you had derivative in respect to x of u times v, two functions, u of x, v of x. You can do f and g if you want to. We had u dv dx plus v du dx, right? So that was the product rule. And if you take a look at the left-hand side, you almost have that. You don't have it quite, right? But you kind of do. And the idea is to multiply through by function mu of x. I don't know why they picked mu, but mu is a Greek letter. We use that mu of x to complete the product rule, and how that mu of x integrating factor solves the problem. Now that would be the long way of doing this. The short way is to memorize the formula that gives you that mu of x and you just plow through the calculation. All right? So technically, when I have my dy dx plus some function p of x times y, and y is a function y of x, right, equals q of x, I can multiply everywhere by this function mu of x, trying to get what we call, right, or what we call product rule on the left. And then we can condense that into a single derivative, integrate, and solve the problem. Now, since this is not an honors course, I don't have to go through all of the steps of, proving this for 20 minutes. I'm just going to give you the mu of x. It's listed in a book. If you have any issues and you're interested, please stop by. It's a cool calculation, but it's, it's not as, oh, they switched the letter on me.
Yeah, I thought it was row.
Yeah, it's row.
That's looking in here, I'm like, oh, it's row.
Yeah, this is a new edition. I didn't look. Yeah, for ages it was mu. Row, yeah. Row of x. Row of x is the new letter they use. Those of you who took calculus, you know that your spherical coordinates use a rho instead of r for the radius of the sphere. Rho is the Greek letter equivalent to our r. Right, and then there will be some calculations here, eventually giving you the formula which you are remembering so you can solve these problems, where the rho of x is equal to the e raised to the integral of px dx. Now, this px is from your differential equation. Sometimes it's a number, sometimes it's a function, depending on the problem. So this is called integrating factor. And it's used to complete the left-hand side of the equation to give you the product rule.
So it sticks p next to the derivative of e of x, and then it
yes.
just drops y on top. Okay, because dy. Okay.
Yes. Well, we're going to do examples, so we're going to see that with values and variables. And it's going to. So I'm just going to pick up any example. It doesn't matter. I'm just going to go into homework. The examples that are given in the book, right? You know all the letters and numbers, so you can just read it, right? I'm just going to do whatever from the book. I don't want to go immediately with some. Well, let's do a vanilla example, and then we'll do one spicier, huh? Yeah. So let's go with number 2. Y prime minus 2y is equal to 3e to the 2x with the initial condition of y0 is 0. So this is something that you get. And now what do I have? So this is the cheapest possible problem you can get, right? Because the p of x is what? Negative 2, not 2y, right? If you look at the formula, p of x is strictly in front of y, and there's a positive sign in front. So our p is negative 2 for this problem. You can't get anything cheaper than a constant for a problem, right? For a p. Remember, it can be cosine squared minus 7. And then, right, good luck from there. Or ln of cosine squared. Just kidding. So I'm going to rewrite this first as equation, and right underneath my linear, so that we can definitely pick up from these two that p of x is equal to negative 2. Once I have that, I am going to compute integrating factor rho of x. Rho of x is going to be e raised to the integral of negative 2 dx. And that is just e to the negative 2x. Now, we are not going to use plus c here. This is just a part of the problem because we will be integrating this later, and it will have a plus c for the whole problem. Remember how for integration by parts, when you integrate the dv part, for v you don't put plus c because there's going to be plus c for the problem? So this is one of those, right, when you do a little partial integral inside of the problem. Yeah, okay, cool. So I have my rho of x integrating factor to be e to the negative 2x. Now, that one will multiply every term of your problem, and it will create a product rule on the left. So, my differential equation is dy dx minus 2 times y, leave some space, equals, and then on the other side I had 3e to the 2x. Now I am going to go and hit each one of these with e to the negative 2x. Now, this is going to be a difficult part because you are not used to doing the product rule backwards. You always do the product rule forward, right? You have two functions and then you say copy the first, derivative of the second, right, and all that good stuff. Well, now you have the answer and you have to go backwards, right? Well, one of the two terms is going to be easy and the other one is going to be tougher. And this is the easy term, because this term you can read as u dv, right? And then you have over here plus v du, but it's not clear what's what in this one. It's really clear what's what here, right? So I'm hoping that you can quickly see, or after some time staring at this, that this is going to be the derivative of ye to the negative 2x. So it compresses into that. Now, another way to deal with this is to literally keep guessing until you guess it correct. So you try and guess, and then you do the product rule, and if it works out, you're done. So integrating factor over here, I'm using that as a function. This is a derivative, which means when I strip the derivative off, I'm only left with a function, with the other function. So that's how I knew. So that's what I call the easy term. This one over here, yeah, I know that the derivative of e to the negative 2x is negative 2 in a chain rule. And then I have the other one that you copy. Whichever way your brain works. You just need to be able to compress those two terms into a product rule. And now, when you multiply these two, the exponents add, you just get 3 on the other side. Because I'm still going to write it. X to the m times x to the n is x to the m plus n. So I add exponents. 2x minus 2x is 0. E to the 0 is 1. 1 times 3 is 3. Wow. Look at that. So now I'm going to copy this, the whole thing. Just make another copy of this. And then we are going to integrate both sides. So now we are going to integrate. No. Okay. So we integrate both sides. we know by fundamental theorem of calculus that derivative and integral on the left cancel, leaving me with y times e to the negative 2x. And on the right-hand side, I get 3x plus some constant c. Are we all bueno with this? Fundamental theorem of calculus, right, cancels the integral and derivative on the left, leaving just the product. On the right-hand side, integral of 3 is 3x. And now, all I need to do is to put e on the other side, leaving y alone. So this becomes 3x plus c in parentheses times e to the positive 2x, because e to the negative 2x would go in denominator, right? And then when you ship it up, it will lose the minus on the exponent. And this is the answer, right? We are done. This is called general solution. Then we have to use the initial condition, right? So now this is what we call general solution. We have that c. But wait, we have y of 0 equals 0. That means x equals 0, y equals 0. Plug in. 0 equals 3 times 0 plus c e to the 0.
C has to be 0.
So in this case, c will be 0, yes. So I have 0 equals c times 1, c equals 0. And this gives me what we call particular solution, the solution. So y is equal to 3x e to the 2x. And that will be what we call particular solution. Yes.
Can we check it?
I was about to go with my favorite. Let's say you care. And clearly you do, right? So you are going to now take the derivative of this. And by the way, what do you have to use to find the derivative of this?
Product rule.
Yeah, right? It kind of makes sense. You use the product rule to solve the problem. You should be able to use the product rule in some sense to check the problem, right? So go ahead, find the product rule, and then stick the differential equation solution and the derivative back into original equation. See if it matches. Next problem, you said trig? No problem. I got you covered. Should we just go in with a cosine or like a cosine cotangent combination or something that it's because the second order oscillations are coming up when we do the mechanical spring mass systems, and they are going to have the wave-like trig behavior. So we could just get our feet wet a little bit, you know, with the first order, where the half of the next chapter is just going to be that and nothing else. So. It stresses you out, I see.
Yeah.
Yeah, anytime you miss trig, please let me know. I'll work it in. You know, it's 16, 17, 18, 19. 19, oh, the cotangent one, I see how it is. Y double prime plus y cotangent x equals cosine x. Lock the doors. Great.
So mu is going to be cotangent x.
P of x.
Rho.
Rho. Well, rho is e to the integral of p of x. All right. We are going to start this problem by our good old comparing this to our formula. Right? We compare this to our formula. Now, what we do is we realize that P of x is cotangent x. And we need to find our integrating factor rho of x as e to the integral of cotangent x dx. Obviously. Now, how do we integrate cotangent x?
Negative cosecant x. Or negative cosecant squared x.
Good.
It was a good one, but you missed a couple of squares there. So what is the way to integrate tangent and cotangent? Frank? Beautiful. We're going to write this as a cosine over sine and use u substitution to integrate to get rho. The answer for this is going to be beautiful. It's going to be ln of blah, blah, blah. And we love that answer because e will cancel ln. And this problem is going to be a tag nicer than the previous one, even though this looks much worse. Anytime when you get the integral that will spit out ln, it will always cancel that e from the base. And you should have a little Fortnite dance. You know the way it goes. So I'm not a good dancer, which is why I do this, right?
You should demonstrate for the class.
I can't do it. I tried. I almost broke I dislocated my shoulders, right? I stop at Beat Saber. All right. So we are going to integrate this. Now, let's say you don't know the answer, right? And you have to integrate the long way using u sub. We can do this integral in blue on the side, cotangent x dx, which is integral of cosine x sine x dx. We have our u to be beautiful, sine x and cosine x dx, which turns the integral into
absolute value of sine x.
Yes, so we have du over u, which is ln of absolute value of
Sine x.
sine x. And then we have the plus c, but we don't worry about plus c in this case because such is life, right? And yeah, ln sine x. Yeah, we're done there. So now our good old. So I'm just going to go like that and then like this. So now rho of x is equal to e to the ln of sine x. And then ln will kill e, and we don't even need the absolute values anymore, right? Because ln is gone. So we're just going to have that rho of x is equal to flat out sine x, which I hope you would argue it's easier than what we had before, right? Or not. So now our problem says dy dx plus y cotangent x, leave some space around because we have to stick this sine x everywhere, equals to cosine x. Now we multiply through by rho, which is sine x.
Yep.
And this is just amazing how well this works out.
It becomes cosine.
Yep.
Sine x.
Plus y cosine x, because cotangent is cosine over sine, and then sine and sine cancel, right? Equals to, usually we write sine x cosine x on the right hand side. And this is where we combine these into a single product rule, which is sine x cosine x. No, lies.
It's going to be y
Lies.
sine x.
Y sine x, yes. Y sine x equals to sine x cosine x.
And then z sub on the other side.
Now is the time. Copy it one more time so you know it's a next step to integrate this, because I don't want this to be all on a pile. There we go. So now we integrate this side, integrate this side. On the left-hand side, again, fundamental trinomial calculus part 2 cancels derivative and integral flat out. We're just left with y sine x. And on the right-hand side, we have this integral, which we can, it's a u sub, right? Is it? It's a u sub, right? You say u equals sine. But then we are in DifEq now, and trig should be our friend. So we can use a trig identity to avoid u sub. It's like cheating. Except that's the next level, you know. Because you know, hopefully, that sine 2x is 2 sine x cosine x. That means that sine x cosine x is 1/2 of sine 2x. So if I have the integral of that, of 1/2 sine 2x dx, then I have a single sign and I don't have to use a u sub to integrate. Pick your poison, right? Doesn't matter which way you do it. So y sine x is equal to, and over here, when you integrate negative 1/4
2x.
cosine 2x, very good.
Plus c.
Plus c, that's where the plus c goes, finally. All it's left is to get y alone. This problem did not have initial value, so we will be done once we have a general solution. So we have negative 1/4 cosine 2x plus c divided by sine x. Now I'm going to do something that is going to trigger some of you. I'm going to multiply by 4, and I am not going to write 4c. I'm just going to leave it as c. And some of you are going to get triggered by that. But as I said, we don't care what the value of that is, whether you write it as a c over 2 or 4c or whatever, because the value of that c is only governed by your initial point. So all of those constants and numbers multiplied into c will be absorbed by c, because c is only computed by, determined by the initial condition. So when I say times 4 times 4, I am going to ignore 4c, and I'm going to just still write c. If that triggers you, go ahead, put capital K instead. Whatever, right? Wait for power series. So first the division line, and then I have negative cosine 2x, still plus c or plus k, whatever, over 4 sine x. And I will call this, this is a particular, this is a general solution. But this is where the problem ends. So your job is to memorize the integrating factor. Your job is to practice a lot to combine product rule backwards into a single expression. The rest is, can you integrate, right? But these are the new things that you haven't dealt with before. So make sure that you are practicing those. Yes?
So is there no way to check this?
Of course you check it. Derivative, stuff it in. This is going to be a quotient rule derivative, right? So you will take the derivative and you will stuff it in the original problem right there on top. Y prime is going with the derivative. Y is going to be the solution. And when you work, yeah, I mean, we have nothing to do. I mean, let's just, right? You love trig. If you say it enough times, you know.
Yeah, okay.
Just keep repeating to yourself, and eventually you will start believing the lie. Okay? And keep going. Then you might even start living the lie. It's like, you know, if you push it further. Y prime is the quotient rule. We square denominator. That's going to be 16 sine squared x. And then 4 sine x times the derivative of the top. Derivative of cosine is negative sine that kills the minus. So that's going to be 2 sine 2x plus c, 0 just dies. Minus copy the top, and that's going to be negative cosine 2x plus c times the derivative of the denominator, which is 4 cosine x. So all we need to do is to stuff this into the derivative, which is, so the way you copy is, as you can see, you select, and then you just bring it here. Really? And then that fails me, and really? Come on. I think the class is over. What do you think?
It's a sign.
It's also cosine.
I get it. Yeah. Quick wit. Poker. Like
Is anyone due to upgrade a crapple phone so I can? I just need to break something. It said poker. Why
Like
is it?
two.
Huh?
Parkway.
Parkway, likely, liked,
Pokers.
pokers, Pokemon.
Poker stars. Pokey. Pokers.
Oh, man.
Poker. It's saying poker. We're subtracting poker.
Yeah, it's just,
Obviously.
that's, let's see if that's gonna be, what I think is just the whole, don't breathe. Don't breathe. Got it. +5 on the next test. All right, so we have that plus the original solution. Oh, should have moved it more. I'm going to regret this now. You have no idea how much I'm going to regret this. Those of you who have places to be, just go. So now that's our y prime from differential equation. Now we need to use our solution, which is minus cosine 2x plus c over 4 sine x multiplied by cotangent x needs to be cosine x. That's it. So we just need to simplify this and we're done. Like that.
That is.
Now, cotangent is what?
Cosine over sine.
Cosine over sine. So all I need to do is to multiply by 4 over here, right? And I already have sine in there. So what do I get? I get now this 16 sine squared x as a common denominator. On top, I have 8 sine x sine 2x plus 4 cosine cosine 2x minus 4c cosine x. And from here, the denominator is taken care of. It's minus 4 cosine x cosine 2x, and then I didn't do the plus 4 in the solution, so that's gonna okay, so plus, when I multiply top and bottom by 4, this 4 distributes, right? So plus 4c cosine x, and all of that needs to be cosine x. So we immediately see that these puppies drop right here. And then this one and this one drop. Maybe I should cross them out with a different color. This is the beauty of trig. Cancels. 8 and 16 cancel, and one of the signs cancel. So I'm left with sine 2x over 2 sine x should be cosine. Yep. Sine 2x is 2 sine x cosine x divided by 2 sine x equals cosine x. Kill, kill. Cosine equal cosine. Woohoo. Done. Yes?
Early in the problem, when we finally started doing the calculus, how did you know which terms to pick as, d over dx?
What do you mean d over?
How do you
Yeah,
decide
right.
what your derivative
Yeah.
is, what the actual product rule is?
Well, the product rule you will always have dy dx, right?
Yeah.
So that one will always spit out this y for your product rule. And then whatever is the function from the other one, but it's a pattern. There are slight, here and there, example or two would be more involved, but experience builds up with ton of homework, and you will be able to tell. So it takes a little bit of time, but dy dx always has to be there because it's a first order linear equation, and that always gives the y in the derivative. and then you just have to figure out the other one. And in the beginning, it's going to take you longer, obviously, because you have to try out just to make sure you got it right? So you will have to do the product rule. But throughout the time, it will get better. So it's experience.
Can you scroll down a little more?
Of course. Oh, the green one?
Yeah.
Okay.
Also, for when you're doing the part where you multiply by 4,
The common denominator? Yeah, I multiplied by 4 because
shouldn't you also multiply by sine?
I don't, because the it's times cotangent, and the cotangent contributes the sine in the denominator. This cotangent here is a cosine over sine. So the sine from the cotangent and this sine make a sine squared. So that's why we only did the 4. We have 8 minutes, and we need to figure out not one more thing, it's just a problem that doesn't fit the formula. What type of massage technique you have to apply in order for the problem to convert from what you have into what you need, right? You cannot use this method unless you have exactly what the formula in the beginning of the lecture says. So if you have anything multiplied into that first derivative, well, this method doesn't work. But maybe you can do something to make it work, which is where a problem like, let's say, 10 kicks in. Now, this book is nice. They give you about 50, 60 exercises, 46 exercises to enjoy, right? So you just go and plow through that. Problem number 10 is one of those that does not match the initial formula. What is my initial formula? It's y prime plus p of xy equals q of x. You have to remember that formula. That is your form of the differential equation you're solving. So let's say you go and you remember your rho. It's useless if you don't know this one with p and q, right? Because rho formula doesn't apply to every differential equation under the sun, right? It applies only for the problems that look like that. Now, our problem 10 doesn't look like that because it has that stuff in front of y prime. So we have to get rid of it, right?
Divide 2x across the board.
Yes. Now that opens a new can of worms. And those worms are division by 0. Once you divide your differential equation by 2x, your x is no longer allowed to be 0 in your solution. Your x is not allowed to be 0 for your initial condition. You can't have y of 0 equals 5. Because y of 0 means x is 0. You just divide it by x. So you have to be careful with these things, right? Makes the computer explode, right? Because a lot of things, right? You try to program something, right, to solve differential equation numeric, you plug this in, right, clearly dividing both sides by 2x, and then you say, and we'll just pick x to be 0 for initial condition. The computer goes, because dividing by 0, right? So I'll do this over here in blood. So divide by 2x means x cannot be 0. That's right. You specify that at the beginning of the problem, and that's just going to trickle down to the rest of the problem. I mean, you just know x can't be 0. Now, that's cool, right? Because independent variable, usually, I mean, sometimes they're 0, but you're not going to look at stuff at 0 time. That's initial case. Also, if you're dealing with length, and right, length is not 0. You can't find the maximum volume of somewhere where one of the lengths is 0. Makes no sense. So there are situations where, problem doesn't have, not having a 0 is just fine. Cool. Once I divide, I get y prime is equal to y prime minus 3y over 2x equals to 9x cubed over 2x. We simplify this mess. Y prime minus. Now, look what I'm going to do. I'm going to say 3 over 2x y is equal to 9/2 x squared. You see how I separated that y on the side to emphasize that your p is what?
-3 over 2x.
Yes. And this x is in denominator.
So it's going to be ln.
It's going to be ln. And this is where we go, woo, right? Because it kills that e. Rho of x is going to be e integral of -3 over 2x dx. So now e, I'm going to kick -3/2 in front of the integral because it's a constant, and then just have e to the -3/2 ln x. Well, first we shove the -3/2 as the exponent to x, and then e and ln cancel. So rho of x is e to the ln of x to the -3/2. Those of you who forgot the ln rule is ln x to the p is p ln x. If you forgot this rule, well, time to review it because it will save your life in this case. And this is where we finally have that our rho of x is x to the -3/2. Now, that's the one that multiplies all three terms, and then we go and we figure out the backwards product rule, and then integrate and do all of the cute stuff. So what is my problem? You go now to your simplified version of the differential equations. Let's use the wood paneling color. And this is where you multiply by your rho, right? So we have our dy dx minus 3 over 2x times y, leave some space, equals to simplified 9 over 2x squared. Now you multiply through x minus 3/2, x minus 3/2, x minus 3/2. Over here, we have to condense all of this into a derivative. On the right-hand side, we just have 2 minus 3/2, which is x to a half, so 9/2 root 2, or root x, or x to a half, whatever, because 2 minus 2, right, 2 is 4/2, 4/2 minus 3/2 is 1/2, so that's root x. Now, remember, I always told you it's always going to be a y, which is there from this one, and the other function here should be this one, right, because when you take its derivative, it will give this as the
Right, or it would be root x, wouldn't it? Because the
yeah.
3.
I don't like it.
Root x.
Copy the first. Yeah, this something went wrong. This is not good. There's an error somewhere in the calculation, which
Professor,
yes.
I think
What?
when class started.
Oh yeah. I know. I'm not sure. Does anyone see this thing?
Everything I did up to that point got to there. But I'm not good. So I wouldn't trust me.
Yeah, we'll have to. This is where we're going to start next class. So try to figure it out. I mean, it's Calc 1, right? try to figure it out, and then we'll start here next class on Wednesday.